paper here. Okay, what I was saying is that the front has all of your basic functions, and then the back, they're a little more complicated functions with asymptotes. So like your exponential, log, rational, and then of course your tangent has asymptotes. Sine and cosine don't have asymptotes, but all the trig is back here together. Okay, so all of the functions we've talked about over the past couple of days are here on this sheet. And we're going to go through, and in this important things to remember box, you're going to jot down some things. A couple of them we may do like a quick little example, but we're going to look at the general form and vertex form and of the equations and all of that good stuff. Because these that we've talked about, this is just the parent function. This can change a lot once we start adding numbers into the equation. We're going to look at where the different numbers can be added and what that means for your function and for the graph. Okay. All right. All right, so the first one we're going to talk about is the linear function. Now, do not write too big in your box. There's several things we're going to put here, so it's better to write small than large, okay? The first thing we want to put is the slope-intercept form of the equation. Y equals mx plus b, okay, where m is the slope, b is the y-intercept, okay? Hopefully y'all remember that from algebra. Okay, and then you want to know, make sure you remember the point slope form. Point slope form of the equation is y minus y1 equals m times x minus x1, where x1, y1, okay, that's any point on the line. And then, of course, m is still slope, like it was in slope-intercept. All right. You also want to make sure you know the slope formula. The change in y over the change in x. So if you have 2 points, you don't have to write every like word for word here. You want to make sure you have the equations though, okay? And instead of like writing m equals slope, like you could just draw an arrow to m and put slope. Okay? Or draw an arrow to, and so I mean these are your notes. Write them how you want them, but okay, so remember that if you have 2 points on a graph, and like you don't probably have to write find slope between 2 points. I think you know what slope formula does, right? It finds the slope between 2 points. So if you don't need to write that little sentence there, don't worry about it. Okay. All right, so y2 minus y1 over x2 minus x1. So the change in y over the change in x. It's your rise over run. Okay, sometimes you'll hear slope referred to as rate of change. Okay, feel good about linear functions? That's what you've been working with the longest. Linear functions, it's the basics. All right, absolute value. Absolute value function. And if I'm going too fast, you can tell me, I'll go back, but I'll also post this PowerPoint on its learning. So you'll be able to go back and look at it there too. And the video of me talking through it to hear my explanations. And if anybody asks questions, hear me answering questions. All right, so we got all the basics about absolute value function, yes, in our notes packet. Okay, but things we need to know. General form of an absolute value equation. Okay, so f of x equals a times the absolute value of b times x minus h. Okay, and then that's all in the absolute value. And then plus k is outside the absolute value. Okay, what you may or may not remember, hk is the vertex. Okay, so that h, whatever's being subtracted from the x inside the function, and the k is what's being added outside the function. So those values there tell you where the vertex is. Remember, the vertex is the point where the graph changes direction. So in the parent function, it's 0, 0, because the graph is decreasing and then it turns and is increasing. Okay, so that point where the behavior of the graph changes, that's your vertex. Okay, and when you have an equation, you can determine that vertex when it's in this general form. Okay, so here's an example. Okay, if I have f of x equals 2 times, times the absolute value of x minus 6, and then minus 2, what would that vertex be? What's the h and the k in that equation? 6, negative 2. Very good. It is not negative 6. There is a minus in the general form of the equation. H is what is being subtracted. So H is 6, positive 6. Okay, now K is what's being added on the outside. Okay, and this would be considered plus negative 2, right? Is minus 2. So 6, negative 2 would be the vertex there. And I don't have that in the PowerPoint. So, I mean, you would need to write that in. The ordered pair, 6, negative 2 would be your vertex. All right, now, the term solutions. Solutions are x-intercepts. When we solve equations, we set the equations equal to 0, right? Like we would plug in 0 for f of x and solve this for x. If y is 0, that means you're on the x-axis, right? So that your solutions are your x-intercepts. So how many solutions could an absolute value function have? Possibly. Could have 2. This graph could definitely cross the x-axis twice, that V shape. Okay, if it's shifted some, it would cross the x-axis twice. Okay, what's the minimum number of solutions it could have? 0. It could have none. Like if this graph shifted up, it would never cross the x-axis. Or it could have exactly 1, meaning the vertex is on the x-axis. Okay, so there is a possibility of 2 solutions, 1 solution, or no solutions. We're going to talk about those possibilities real fast. If when you're solving your function, your absolute value function, if the absolute value comes out to be a positive number, then you're going to have 2 solutions. Okay, because if you get like the absolute value of x is 2, well, x could be 2 or negative 2, right? Okay, so you could have 2 solutions in that case. Now, when the absolute value comes out to be 0, there's only 1 solution. Now, if the absolute value comes out to be a negative number, that doesn't make sense. There's nothing I could plug in for x and take the absolute value of it and get a negative, because absolute value always comes out positive, right? So when you're solving, you have the absolute value set equal to a negative, that means there's no solution. That graph does not cross the x-axis. Now follow? And this is just what I said a second ago. If you need to write it down, you can. You may not need to. That the vertex is the point where the behavior changes, the increasing, decreasing behavior. If it depends if the negative was in the place of the A or the B, like if it was outside the absolute value or inside the absolute value. And we're going to get into transformation rules a little more detail next week and talk about how does A, B, H, and K, how does that actually affect my graph from the parent function. So yeah, y'all learned all those transformation rules in Algebra 2, but we're going to do some notes going back over those to refresh your memory on transformation rules. So yeah, we'll talk about that some more next week. But just in general, things to remember, this would be it. Now, is there another function that would have that same situation with You could have 0, 1, or 2 solutions. Yeah, the quadratic. Okay, so we're going to talk about the quadratic next. And one of the things that we're going to add into our need to know or things to know is going to be about the possible number of solutions. But first, we want to talk about the different forms of the equation. Okay, you can have vertex form. Okay, and this looks really similar. It has the A, B, H, and K. Okay, so like the absolute value was just set up, where A is multiplied outside, B is multiplied inside, H is subtracted inside, and K is added outside. Okay, but instead of the absolute value bars here, it's parentheses squared because it's a quadratic, not an absolute value. Okay, so when you're in that form, you can still see the vertex HK. Now, often quadratics aren't in vertex form, they're in standard form, which is ax squared plus bx plus c. Okay, this is like when we were factoring, we had quadratic form trinomials that we did a lot of factoring practice with. Okay, that's called standard form. Now, if your equation is in standard form, you can't see the vertex. Okay, like you can just pick it out here using H and K. So you got a little bit of work to do to find the vertex. You would have to do negative b divided by 2a, and that's going to give you the x value of the vertex. Okay, that's going to tell you where this line of symmetry that cuts your graph in half. Okay, negative b divided by 2a. You would use the b and a value there, and that's going to give you the x value of the vertex. And then you plug that back in for x in both places where x is, and you solve and you see what the y value is. And then you have your vertex. Okay, so vertex form is nice because you can just see the vertex. Standard form, you got to do a little bit of work to get the vertex. Okay, so let's talk about those solutions. The same thing with that we said with absolute value. There's 3 possibilities. You could have 2 solutions, 1 solution, or no solution. Okay, it could cross the x-axis once, twice, or not at all. Okay, and it's a similar check as absolute value. If you get down to the x squared portion, okay, your whatever is inside your function squared, and that's a positive number, okay, you have a maximum number of, you can have 2 solutions. That's the max number. Now, if you get down to that point and it's equal to 0, okay, you're only going to have 1 solution. But if you get down there and that's set equal to a negative number, that doesn't make sense, does it? Nothing squared is going to give you a negative number. So that means there's no solution. It's not going to cross the x-axis. And again, the same thing, the vertex is the point where the behavior of the graph changes. Be all set to finish writing. Pretty good? All right. So next we're going to look at the square root function or the radical function. So this is the first one yesterday when we were going through these. This was the first one that had a domain restriction, right? Okay, it did not go negative infinity to positive infinity for the domain. Okay, so this is a different function than the others. It does not have an arrow on both ends. It has an endpoint and then goes on forever in one direction. The general form looks very similar to the others, except instead of absolute value bars or the parentheses squared, it's a radical that the b times x minus h is under. That's a radical function or a square root function. HK is still the vertex. Now, is that really a vertex? This doesn't change direction. And technically, yeah, this is an endpoint. we can call it a vertex. But this is the inverse function of the quadratic, which it's like half of that parabola. The other half of the parabola would be down here in quadrant 4. And so then, yes, this would be a vertex if you saw the other side of that. We don't see it though, because then this wouldn't be a function. It wouldn't pass that horizontal line test. Remember we used to do. We're not going to have those negative y values here, because when you take the square root of x, we're only looking at the positive square root of x. If we put a plus or minus in front of this and we looked at the negative, we would see the other half of that, but then it wouldn't be technically a function. Anywho, just explaining why we still use the term vertex there. All right, now, if this was your equation, what would the vertex be? Just an example to look at. 5, 3, very good. It'd be positive 5, positive 3. Okay, 5 is the H, 3 is the K. Now that would mean that this graph here, instead of starting at 0, 0, it's at 5, 3. Okay, right here where my arrow is would be the beginning of the function. Okay, and nothing else is happening to this. There's no negatives or any numbers being multiplied or anything like that. So it's just this same shape. It's just shifted over and up. Okay, so the vertex would be at 5, 3. What would that mean for the domain and range of the function? What would be the domain and range of this example function? We said the domain of the parent function here was 0 to infinity, right? And that's because the vertex is at 0 on the x, for the x value. What would be the new x value of the vertex? 5, right? So what would the new domain be? 5 to infinity. And it would still have the bracket, just like this, because the 5's included. What would the range change to? Instead of 0 to infinity, what would the range of this one be? 3 to infinity. Good, because 3 is the y value of the vertex. So I would jot those down here. So the domain would be 5 to infinity, including 5, and the range would be 3 to infinity, including 3. 5 to infinity with a bracket around the 5. Good? All right, the next one we're going to look at is the cubic function. Okay, so we have our cubic function, y equals x cubed. We looked at this yesterday. Here is, it's typically seen in standard form like this. Ax cubed plus bx squared plus cx plus d. Okay, similar to the standard form of the quadratic. Okay, but we've got one extra term. We've got a cubed term also. Okay. Now, this is either going to have one root, and root is just another term for solution, where it crosses the x-axis, x-intercept. We can use solution, root, x-intercept, zeros. Those all mean the same thing. Okay, but a cubic function is either going to have 1 or 3. There's no way for it to have 0. It's definitely going to cross the x-axis. Now, for it to have 3 roots, these, see this point of inflection here? Let me actually pull this up. Okay, there's no vertex here, but there is this point of inflection, okay, here where kind of the shape of the graph changes a little, like it's still increasing, okay, but the concavity of it changes a little. Okay, that point of inflection to the left and right of that, these can be pulled up and pulled down, which would make it could cross, come back down, cross again, and then go back up and cross again. So there could be 3 roots. Okay, so it's going to have 1 or 3 roots or solutions. Okay, and here's a picture of what that could look like. Okay, so that point of inflection was in the middle here, and this got pulled up and pulled down. Now, this still only has 1 root, but if this was shifted down, you could see that it could possibly cross at 3 points. Everybody see that? Okay, it's gonna have 1 or 3 roots. Everybody okay with cubic? All right, cube root, things we want to know. General form, okay, very similar to the radical or the square root functions, general form, except it's a cube root instead of a square root. Still have the a, b, h, and k. Now, we don't have a vertex. Same thing with cubic, didn't have a vertex, but it has a point of inflection. And that point of inflection is the hk. Okay, so the point of inflection in the parent function is here at 0, 0. Okay, but as the graph changes, that's at hk. All right, now it is only possible to have 1 solution here, 1 root. This graph can only cross the x-axis once. It will cross it once. Because it's continuous, it goes on forever. It'll eventually cross somewhere. Okay, so that should be the whole front side of that filled in. Everybody good with that? All right, so let's flip it over and take a look at the back. I'm actually going to stop this video here, though. So I'll do this in 2 parts for the videos. Give me a sec.